Welcome to episode 3 of our series, Creating Conscious Systems Through RL Flow. I'm your host, Bella. In our last episode, we delved into the intricate web of consciousness and matter, laying the groundwork for our journey into understanding RL flow theory. Today, we take the next step on this journey as we explore the exciting world of biological and artificial systems and how they intertwine. The focus of this episode, Building Bridges, Biological and Artificial Systems, is to illuminate the connection points between the organic, as represented by our own brains, and the synthetic, as represented by computers and artificial intelligence. Understanding this interface is crucial in our quest to create conscious systems, as it enables us to understand how the organic and the synthetic can not only coexist, but thrive together. In this episode, we will be exploring this interface, investigating real-world case studies, and uncovering the myriad of challenges and opportunities that lie ahead in this cutting-edge field. So, without further ado, let's delve into the mesmerizing interface between biological and artificial systems, and uncover how these two distinct fields can collaborate to push the boundaries of what we perceive as possible. As we delve into our exploration, the first concept we need to unpack is what exactly we mean by the interface between biological and artificial systems. In the broadest sense, an interface refers to the point at which two systems meet and interact. It's where information, signals, or energy are exchanged. When we talk about the interface between biological and artificial systems, we're referring to the various ways in which organic, biological entities like our bodies or brains interact with synthetic, non-biological entities such as computers, robotics, or artificial intelligence. This interaction can take many forms, from the simple act of a human using a computer or smartphone, all the way to more complex and direct interfaces, like the kind we see in cutting-edge fields like brain-computer interfaces, or BCIs. These are systems that allow for direct communication between the human brain and an external device. However, the interface isn't just about communication or interaction, it's also about integration. It's about the fusion of biological and artificial systems in a way that leverages the strengths of both to create something new and extraordinary. This may include augmenting human capabilities, creating more sophisticated AI systems, or even potentially building conscious machines. As we navigate this series, we'll explore these concepts more thoroughly, but for now, the crucial takeaway is this. The interface between biological and artificial systems is where the organic meets the synthetic, where the lines between the natural and the artificial begin to blur, and where the potential for extraordinary advancements in technology and understanding lie. In order to fully grasp the concept of the interface between biological and artificial systems, we need to first understand how these individual systems function. Let's start with biological systems, specifically the most complex of them all, the human brain. Our brain is a masterpiece of evolution. It's composed of approximately 86 billion neurons, which are essentially the building blocks of the brain. Each neuron can form thousands of links with other neurons in complex patterns, creating a vast and intricate network of connections. This network is dynamic and constantly changing, influenced by everything from our genes to our experiences. These connections, or synapses, are the basis of how we learn, remember, perceive, and interact with the world. Now let's turn to artificial systems. In the context of our discussion, we're primarily referring to computers and artificial intelligence. The central processing unit, or CPU, is the brain of a computer. It's where most calculations take place. In terms of function, you could compare the CPU to the human brain. A computer operates on binary code, using strings of ones and zeros to represent information. Software programs provide instructions that the CPU interprets and executes. This is in stark contrast to the analog, parallel processing of the brain, which doesn't operate on binary code and where many processes happen simultaneously. AI, or artificial intelligence, takes the concept of computing a step further. In its most basic form, AI involves the development of computer systems that are able to perform tasks that usually require human intelligence. This includes tasks like understanding natural language, recognizing patterns, learning from experience, and making decisions. AI algorithms, particularly those using machine learning, are designed to learn from data. The more data they're exposed to, the better their performance. This is somewhat analogous to how our brain learns from experience, but there are still significant differences, particularly in the types of tasks each system excels at and how they process information. In the following segments, we will delve deeper into the fascinating opportunities and challenges that arise when we try to bridge these two vastly different, yet remarkably similar systems. As we attempt to bridge the gap between biological and artificial systems, it's crucial to appreciate both their similarities and differences. These characteristics not only shape how these systems function in isolation, but also how they could potentially interface and even augment each other. In terms of processing power, artificial systems such as supercomputers are capable of performing calculations at an astonishingly fast pace. For instance, Fugaku in Japan can perform more than 442 petaflops, or quadrillions of calculations per second. On the other hand, the human brain's speed isn't as straightforward to quantify. It doesn't perform calculations in the same linear, step-by-step fashion as a computer. Rather, it works through a vast, complex network of neurons firing all at once in parallel to process information. This allows the brain to excel at tasks like pattern recognition, emotional understanding, and decision-making under uncertainty, which are areas where traditional computers and even advanced AI can struggle. Now, if we shift our focus to energy consumption, the brain is an undisputed champion of efficiency. Despite its immense processing power, the human brain uses approximately 20 watts of energy. In stark contrast, supercomputers consume enormous amounts of energy. For instance, Fugaku uses around 29.9 megawatts, or nearly 1.5 million times the energy of the human brain. The potential capabilities of both systems are fascinating to contemplate. Artificial systems, especially those harnessing AI, are increasingly being used to perform complex tasks, from diagnosing diseases to driving cars. They excel at processing vast amounts of data quickly and accurately, and their capabilities are continually expanding as technology evolves. The brain, meanwhile, despite centuries of study, continues to baffle and amaze us with its capabilities. From creativity and abstract thought to emotional intelligence and the ability to learn from experience, the brain possesses abilities that we're still struggling to replicate in artificial systems. The concept of a brain-computer interface, or BCI, is a powerful example of how we're already building bridges between biological and artificial systems. Essentially, a BCI creates a direct communication pathway between an enhanced or wired brain and an external device. BCIs are often directed at assisting, augmenting, or repairing human cognitive or sensory motor functions. They have been used for years in the medical field, helping those with physical or neurological impairments. For example, BCIs can enable communication for individuals with severe speech or motor impairments, or provide functional recovery for those who have had strokes or spinal cord injuries. So, how does it work? In one common type of BCI, electrodes are placed on the scalp to pick up the electrical signals generated by the brain. These signals are then decoded and translated into commands that control an external device, such as a computer or a prosthetic limb. But BCIs can also work in the opposite direction, sending signals from an external device back to the brain. For instance, in a cochlear implant, a kind of BCI used to treat profound hearing loss, signals from a microphone are processed and sent as electrical signals to the auditory nerve. While these applications are impressive, they represent just the beginning of what's possible. As BCI technology advances, we're starting to see more sophisticated interfaces. Elon Musk's company Neuralink, for example, is developing ultra-thin threads that can be implanted into the brain to detect and stimulate neurons with unprecedented precision. This could potentially be used to treat a wide range of neurological disorders and may even allow for novel forms of communication or enhanced cognitive abilities. There's no doubt that the future of BCIs is incredibly promising. However, it's also important to keep in mind the ethical considerations and challenges that come with this rapidly advancing technology, a topic that we'll touch on in later episodes. Another compelling example of the intersection between biological and artificial systems is the concept of deep learning and artificial neural networks. This approach to artificial intelligence is directly inspired by the way our brains work. Just like a biological brain consists of interconnected neurons, an artificial neural network is made up of a web of artificial neurons, or nodes. These nodes are organized into layers: an input layer to receive data, an output layer to make decisions or predictions, and in between them, one or more hidden layers to process the inputs and pass on signals to the next layer. Much like the synapses in a biological brain, each connection between nodes in a neural network carries a weight. These weights shape the output of the network by determining how much influence each input should have on the final decision or prediction. The process of training a neural network involves adjusting these weights based on the feedback the network receives. If the network makes an incorrect prediction, an error signal is sent back through the network, prompting it to adjust its weights. This is analogous to the way our brains learn from mistakes and is known as backpropagation. Deep learning is a type of machine learning that uses neural networks with many layers, hence deep. These deep networks are capable of learning from unstructured or unlabeled data, making them very powerful tools for tasks such as image and speech recognition, natural language processing, and even game playing. A famous example is Google's DeepMind AlphaGo, which used deep learning to become the world champion in the board game Go. So, you can see that the bridge between biological and artificial systems is not just metaphorical. By taking inspiration from the structure and function of the brain, we've been able to develop powerful AI systems that can learn and adapt. And as our understanding of both biological and artificial systems continues to grow, we can expect this trend to continue, leading to even more sophisticated and capable AI. Our third case study brings us to the cutting-edge field of biocomputing, which seeks to leverage the computational power of biological systems. One of the pioneers in this field is Professor Thomas Hartung from Johns Hopkins University. Hartung and his team have been using organoids, tiny 3D tissues derived from stem cells, in their attempts to revolutionize the computational landscape. To give you a bit of context, organoids are self-organizing structures that mimic the complexity of an organ. Scientists have produced organoid cultures for various organs, including intestines, liver, pancreas, kidneys, prostate, lung, optic cup, and most importantly for Hartung's work, the brain. Starting from 2012, Hartung's team began to grow and assemble brain organoids using human skin samples that had been reprogrammed into embryonic stem cells. Each of these organoids, about the size of the dot on the letter I, contains approximately 50,000 cells, including neurons and other structures that sustain basic functions like learning and memory. It's this potential for basic cognitive function that makes organoids an exciting prospect for building futuristic computers. While human brains might be slower than modern computers in tasks like arithmetic, they excel in logical decision-making. Moreover, the storage capacity of the human brain, estimated at around 2,500 terabytes, is enormous. This computational potential, combined with the energy efficiency of biological systems, is what Hartung's team is trying to harness. To put things into perspective, Frontier, a supercomputer installation in Kentucky that cost $600 million and covers an area of 6,800 square feet, only surpassed the computational capacity of a single human brain in June of the previous year. And it did so while using 1 million times more energy. Imagine the potential if we could match or even surpass that computational capacity in a much smaller and energy-efficient package. It's important to note that this research is still in its infancy, and there is a long way to go before organoid intelligence can compete with any type of computer. However, the potential benefits of biocomputers, being faster, more efficient, and more powerful than their silicon-based counterparts, and requiring a fraction of the energy to operate, make this an area worth investing in. In addition to their potential in computing, brain organoids could open up new opportunities for drug testing, especially for neurodevelopmental disorders and neurodegeneration. This adds another dimension to the bridges being built between biological and artificial systems. As exciting as the potential of bridging biological and artificial systems is, it's not without its challenges. For one, there are technical issues. The intricacies of replicating biological systems, especially something as complex as the human brain, are immense. We're dealing with processes that have been honed by millions of years of evolution, and our understanding of them is still developing. Translating this to a functional artificial system is an incredible feat of engineering that will likely require significant advances in several scientific fields. Second, there are ethical concerns. At what point does an organoid become conscious? And if it does, what rights should it have? These questions may seem speculative or even outlandish, but they are debates we need to have as we push the boundaries of technology. Moreover, the potential misuse of these technologies is a serious concern. Imagine, for instance, the prospect of cognitive enhancement beyond normal human capabilities. It could open up societal divisions, ethical debates, and even potential threats to our collective security. Lastly, there are potential unforeseen consequences. Anytime we deal with complex systems, especially those that we're integrating with the equally complex systems of the human body, there's a risk of unintended side effects. What if an AI integrated with a brain organoid developed a fault or started malfunctioning? How would we deal with such a situation? However, despite these challenges, the opportunities are just as immense, if not more. Imagine a world where we could harness the computational power and energy efficiency of biological systems. We could revolutionize fields from AI to medicine and potentially unlock new technological capabilities that we can't even imagine today. In addition, the potential benefits in the field of healthcare are significant. The ability to effectively model diseases on a patient-by-patient basis, to test drugs and therapies with a degree of precision currently unimaginable, and to explore the mechanisms of complex disorders like autism could drastically improve the quality of life for millions of people. As we move forward, we need to navigate these challenges and opportunities with care, engaging in continuous dialogue about the ethical and societal implications, and pushing for regulations that ensure these technologies are used in a manner that benefits all of humanity. There's no denying that the successful integration of biological and artificial systems could open up an array of opportunities that may seem like science fiction today, but could very well become a reality in the near future. One of the most fascinating prospects is the advancement of artificial intelligence capabilities. By successfully modeling and integrating the intricacies of biological neural networks, we could potentially create AI systems that are much more powerful and efficient than anything we currently have. These systems could not only process information at a level comparable to human brains, but also approach problem solving in ways that we can't even fathom right now. The field of medicine could also see revolutionary changes. We've already touched upon the potential of brain-computer interfaces and their current applications. Imagine taking that a step further. Systems that could monitor your health at a cellular level, detecting issues long before they become problems, and suggesting targeted treatments. This could potentially allow for personalized medicine at an unprecedented level, vastly improving patient outcomes. Finally, let's not overlook the potential for exploration in consciousness studies. The mysteries of consciousness are among the most profound questions in science and philosophy. By creating artificial systems that can emulate biological consciousness, we could potentially gain new insights into the nature of consciousness itself. This could not only advance our scientific understanding, but also provoke deep philosophical and ethical discussions about the nature of consciousness, sentience, and our understanding of what it means to be a self. Of course, as with any technological leap, the journey won't be without challenges. But as we navigate these challenges, we'll also be pushing the boundaries of our understanding and opening up new vistas of knowledge and possibility. As we venture into this brave new world of integrating biological and artificial systems, it's imperative that we strike a balance between our pursuit for technological advancement and our responsibility towards ethical considerations and societal impacts. In our excitement to unlock new potentials, we must not overlook the ethical implications of our work. As we increasingly blur the lines between the biological and the artificial, we grapple with questions about consciousness, identity, and the rights of potentially sentient artificial beings. These are not just abstract philosophical questions, but real issues that we must confront as we advance in this field. Moreover, we need to carefully consider the societal impacts of these technologies. For instance, while advanced AI systems could revolutionize industries and make our lives more convenient, they could also lead to significant job displacement. And while brain-computer interfaces could improve the quality of life for people with disabilities, they could also be used for nefarious purposes if fallen into the wrong hands. It's crucial that we involve a wide range of stakeholders, scientists, ethicists, policymakers, and the general public in these discussions. The decisions we make will not only shape the direction of scientific and technological progress, but also have profound implications for our society and our understanding of what it means to be human. So, as we build these bridges between the biological and the artificial, we are also building bridges between different disciplines, between science and ethics, between technology and society. And as we navigate this intricate web, we must remember that our ultimate aim is not just to advance technology for the sake of technology, but to use it as a tool to enhance our understanding, to improve human lives, and to create a better future for all. As we conclude our exploration of the intriguing bridges being built between biological and artificial systems, let's take a moment to reflect on the fascinating journey we've embarked upon today. We started by defining the intricate interface between the organic and the synthetic, where complex biological processes inspire and inform groundbreaking technological advancements. From brain-computer interfaces to deep learning systems modeled on our own neural networks, and the exciting new frontier of biocomputing with organoids, we've seen that the potential for integration is not just promising, but already in progress. Yet, as we stand on the precipice of such groundbreaking discoveries, we also recognize the challenges that lie ahead of us. Technical hurdles, ethical considerations, and potential societal impacts are all part of this complex equation. But it's precisely these challenges that make the journey worthwhile and the rewards potentially transformative. As we look forward, we glimpse a horizon teeming with opportunities. The prospect of advanced AI capabilities, improved medical treatments, and a deeper understanding of consciousness are just a few of the potential benefits that may arise from this fruitful symbiosis of biological and artificial systems. But our journey is far from over. As we wrap up today's episode, I invite you to join us next time when we'll dive into a deeper layer of this fascinating topic: conscious energy. How is it defined in the context of RL flow? How does it interact with physical matter and information? What's the current state of research in this area? All these questions and more will be explored in our next episode: Conscious Energy, the Building Blocks of Experience. Until then, keep contemplating the marvels of RL flow and stay curious about the world around us and within us.